Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Moein Mosleh with us today. Hey, Moein.
Hi, Frank.
How are you today?
Well, I'm good. Thank you. How about you?
On this May 5th, 2021, I'm doing pretty good in Phoenix. It's starting to heat up. We're probably going to hit 35°C, 37°C here in about 2 days or so. So we're on the upside of a warming. And how about you? What's your geolocation?
Well, I'm in Shiraz. It's a city in the south of Iran. It's known for the poets, gardens, flowers.
And astronomers.
And it's known for the wine as well, Shiraz wine.
Oh yeah. Yes.
Yes.
I've actually had Shiraz before. It's very nice. So you look like you're in your office there.
Yeah, I'm in my office at the moment.
Very cool. Nice bookshelf. I recognize some of those. Astronomy text.
Some of them are old catalogs of stars. Actually, I'm in the office, which is its building is a Biruni Observatory building in the Shiraz University. It's a 45-year-old observatory, which was founded by two persons in Iran. And one of them were American, actually. They were doing some observing variable stars, especially eclipsing binary stars. It has a 50-centimeter telescope. So I'm in that office actually.
Very cool. So are there still operational telescopes at the office? Okay.
It is operational. Yes, it's still operational. But we have a light pollution as well. So
yeah. So they're optical.
Yeah.
Okay, cool. Yeah. Very cool. So it's a historical place. That's awesome.
Yes.
Very good. Cool. So Moein, what do you like to do for research?
Well, I study galaxies, actually. Galaxies are complicated objects. They have stars, dust, dark matter, gas coming in and going out, black holes. So what we would like to know is to understand how these objects form. So there are many people actually involved in this business. And as you know, when we look in the local universe, we see a diverse of these sort of galaxies in terms of their morphology, in terms of their physical properties, such as their rate of star formation, their gas properties, their kinematics, many other properties. So they are cool objects to study, actually, and so we are in a very.
I'm always really happy when people get passionate about the topic they study. So it's very nice to hear you say they're quite cool and you're fascinated by them. So I'm always kind of curious before we get going, how people sort of get into the field they get into, right? Because there's 1,001 topics one could study in astronomy.
Yeah.
So how did you get into galaxy and galaxy formation?
Well, I think when I was doing my master degree, I realized that there are a range of actually topics. I was in the UK when I was doing my master in Sussex University. First, I was very fascinated by the cosmological problems like dark energies, etc. And then gradually I realized that this to study the cosmology, observational cosmology, you need to know more about the galaxies. And gradually I get involved into this business. And then when I moved for my PhD, I study this explorer in this field.
Cool, very cool. Thank you for sharing it. And that is going to bring us to this very lovely APJ article, Galaxies Since Z = 2, from the perspective of stellar mass distribution within galaxies. And Moein, take us away.
Yeah, the what in this paper we're trying to do is to understand basically how the stellar masses are assembled. As we know, when we look into the normal galaxies in the local universe, we see that galaxies, for example, have a different distribution of their stellar masses inside them. For example, many galaxies, many massive galaxies have a concentration of the stellar masses inside, in the center of them. And then in the outside, you might have a low density of this mass distribution. And also when you look into the morphology of the galaxy, you see that some of the galaxies are like ellipticals, and some like spirals. They have a different stellar mass distribution because the light and their morphology is the reflection of the mass distribution within these galaxies. So in order to understand how this mass has been assembled, why they are not flat objects, so we need to look into details of these systems, and also we have to look into the galaxies where exist in the earlier time, actually looking into them at the higher redshift in terms of the what it's common to say. So there are different mechanisms actually to explain these things, and actually is proposed to explain the formation of this structure or substructures inside the galaxies. And for example, some of the galaxies for the gas compaction, for the gas came into the center, lose the angular momentums, came to the center, or some of the galaxies might actually form, some of the structures might form by mergers of the subcomponent or the main galaxies. So we are very interested to know how these systems have been assembled, and what are the paths for forming these different systems as we look into as they have been formed since the Big Bang. So basically what we wanted to do is to understand this better. People normally for this sort of analysis, look into the light distributions of the galaxies. This would be much easier and very basically straightforward to do that. But the problem is that the distribution of the light is not a direct representative of the light distribution, because we know that within the galaxies, the stars have different ages, different metallicities, and the dust has been not uniformly distributed.
Indeed.
And so this caused to have somehow a mass to light ratio variation inside the galaxies. So to better understand that, it's better to convert the light into the mass distribution, and assuming this sort of mass to light ratio variation within the galaxies. This would inform us better how the mass, stellar mass, I mean, has been distributed over the galaxies. So the challenge is that when we wanted to convert the light to the mass, we have many difficulties. For example, the best way to do this is to go and do a spectroscopy with IFU, integral field spectroscopy, to do the details and to know the exact mass to light ratio inside the galaxies. But this is very expensive, especially when we wanted to actually go to the higher redshift, and we need to spend much time to observe this a large sample of the galaxy for this sort of analysis. So what we actually do, we try to do, is to find a way, economic way, basically, to have a large sample of the galaxies and drive the morphology in terms of the mass distribution. And it was also interesting that there were not many actually works, papers, which has been done this sort of analysis, because it's very time consuming and you want to do this analysis. And
yes.
So this is one of the goals of this paper that we intended to do. And the other was to, when we have this mass profiles, mass distribution map of this mass morphology of the galaxies, then we also wanted to know more about their morphology. We were looking for some parameters to say more about the central part and the outer parts of the galaxies to understand better their evolution. Yeah, so that was the motivation for writing this paper and working on a large sample and provide a catalog for the community for their further analysis or comparing to the simulated objects. That was the introduction part of my talk.
Cool.
So, okay, then we can move to the, for example, figure 1 to see how we select the galaxies.
Okay.
It's in page 3, I think.
Yeah. So we may have a little bandwidth lag over.
Sorry, it's here.
Figure three. Okay.
Figure 1. Sorry.
Oh, you want figure 1? Okay. Sorry.
Yes, figure 1. Yes, that's it.
Okay.
So that's just we try to select a large sample of high redshift galaxies. We wanted to compare galaxies at different redshift. And so we select a large sample from candles and 3D HST analysis, the imaging that's obtained from the Hubble Space Telescope. And over 5 fields. These are the main high redshift fields that people are normally use, the Cosmos, UDS, AGS, good fields. So, and this would help us remove cosmological biases because they have from different directions. So, and so we select galaxies with stellar masses more than 9.10 to the 9.8 and above a redshift, up to the redshift of 2, basically. The reason that we have this selection is based on our simulation to show how robust are the analysis. So we could not move more than redshift of 2, and we could not select galaxies less than this stellar mass range, because we would have a very large uncertainties on the parameter measurements. So that's basically the figure 1 is showing the sample selection of our from different fields or different ranges.
One question. There's sort of this very noticeable drop off in the number right around 1.3. It's sort of a vertical line in this plot. Why is that?
Well, the reason is that in our analysis, we have realized that 2 of our fields are deep enough for redshift more than 1.3. And 3 of them are not good enough for this analysis. So we select 2 fields for this redshift range, 1.3 to 2. That's why the number of the samples drops after redshift of 1.3.
Okay, cool. Thank you.
You're welcome. And so this is a selection, and the next figure is not a very serious one. We're just showing that if we remove those which are not, we cannot measure the stellar masses reliable, would not affect the basically the distribution of our samples. That's why we just show this to the community, that this will not change the final results of the paper.
Right.
So in section section 3 basically, which we started to create 2D stellar masses. I just briefly mentioned there are many people try to convert mass profiles in different ways, but we choose to be very direct and remove and try not to use some assumptions, pre-assumptions. So we basically try first to convert the light maps, light profiles to the light images to the stellar mass maps, using pixel by pixel spectral energy distribution fitting.
Okay.
So that was a bit a challenge because we have more than 5,000 galaxies, and each galaxy was sometimes like a catalog for us. There were thousands of pixels inside them. So that was a challenge because it took us a lot of time to do this analysis. But we used the 3D HST. This was a very high resolution images that we have. And for each pixel, we do SED fitting. And then we create a stellar mass maps, which we can see in figure 3, basically. Yes.
Okay.
Just a sample of the systems that we see today is just basically, you see in this, in these images that in the left side is the color images of the galaxies, and in the right side is the basically the stellar mass maps that derive directly from SED fitting.
Okay.
So these are very smooth maps, and stellar mass are something a bit robust in SED fitting. So this would be very interesting. When I look into these systems, into the stellar mass maps, I was very excited because it shows some features sometimes, and that was very interesting.
Yeah.
But the first step was to basically test how robust are these mass maps, and how robust are all this step of the measurement. So the next figures, figure 4 and 5, were just to compare the total stellar masses coming from SED fitting with the masses, for example, in the figure 4, with the masses, if we just sum up for each pixels. So this is basically the mass, unresolved mass compared to the resolved mass. And so in the lower redshift beams, we have a little, basically, so about 0.06 takes difference. This is not significant systematics. But when we move to the higher redshift beams, yes, in the right side, we have a larger systematics between this resolved and unresolved stellar masses. That was quite interesting for us because, and we couldn't solve this because, but it was something that we can bring to the community to look into that. Perhaps a lot of assumptions, maybe simple assumptions or more very complicated assumptions could contribute to these differences, but that would be interesting to look into that because, for example, if we use a simple star formation, exponentially star formation history, which might not be very good, but that's something that we can do. Maybe this is the reason, or maybe we have to have a observation in longer wavelengths, which we didn't have because the resolution was not matched. We have observation, but the resolution is not good enough that we could use them.
Okay.
So this was, and there is a discrepancy. I mean, people are not agreeing. This some people find the differences, and some people could not find any differences. But that was one of the results that we wanted to show with the community and share this to see how we can basically come up with the true mass distribution at each redshift.
Very nice.
Yeah, and the figure 5 is just, we wanted to show that this does not depend on the specific star formation rate of the galaxies, as some people claim that.
Yep.
But beside that, I mean, we just found that I don't want to go now in the details, but we have this analysis with simulated objects, and we show this in the appendix, which I don't want to go this right now. But this was not because our method was wrong. This was just maybe because some assumptions that we don't know at the moment, but we have to know it in the future. Okay. Nevertheless, the next step was to basically derive the structural parameters for these galaxies. I mean, the size of the systems, how the stellar masses are concentrated, etc. So that was the next section 4, basically, that we wanted to measure them. It's yes, section 4. Okay. And this was also a challenge for us because the stellar mass maps are a bit noisier than light profiles. So
smooth them.
We come up with 2 methods to basically test, to basically measure this the structural parameters. And we describe both of them, but we choose one as a fiducial basically method, and we describe it in the main part of the paper. And that was the method is to basically run an ellipse on this stellar mass maps and convert them, these 2D dimensional mass maps, to 1-dimensional. And then we build a large grid of models in 1-dimensional, in the same way that would be in a large range of the size and Sersic parameters, which because we basically fit the Sersic models to these systems. Okay. And so we compare the models and observations. This is about 30,000 models. So this was also a bit time consuming to compare these systems, but we wanted to make sure that we do not to reduce the uncertainties in this analysis. So the figure, I think 6, if I remember.
Figure 6.
I think it's 6. Yes.
6. These are your median stacked relative errors.
Oh no, this is not. This is just to show the errors, which we don't need to go into this. Figure 7, basically. Yeah. Yes. Yeah. Figure 7 is just compare of the mass profiles with the best fit models. Best fit models are in orange lines, and the blue ones are just the best fit models that we basically show for the samples that we saw in figure 3 for the object stellar masses. So for this all analysis, we've done the simulations to make sure that our method works well, not going into trouble afterwards, which we actually added to the end of the papers. But I will describe a little bit about them at the end. But basically, this is just a comparison between the models and the observations that the mass profiles that we drive. So, and showing that the fitting is relatively acceptable and good for enough for our analysis. So we use what we basically drive is the half mass sizes and the Cerseic profiles of these galaxies. Cerseic is a parameter to show how concentrated the stellar mass is, and the half mass is a place where the half of this total stellar mass exists. And then we also use some recent work of people to basically measure the sizes of the 20%, not the 50%, because half mass is 50% of the total stellar masses. But we look into the size where 20% of the total masses exist, and also the sizes which have 80% of the total. So these two would be very helpful to know more about the changes in the central and the outer part of the galaxies. So that was would be also interesting, because half mass is just a single number, but when we combine this with the 20% and 80%, then it would be help us to understand if the inside the galaxies are changing, the density of the inside is changing, or the density of the outside. Sometimes the half masses doesn't change, but the outside and the inside both are changing, so that cancel out. So that was and so we use these two parameters, and then at the first step for showing how meaningful this analysis was to show the size-mass relation of the galaxies, which is in figure 8. Size-mass relation is also economic relation for many people, and so this is very can be used for many studies. And
20.
Yeah,
okay. Good.
So what we see here is a couple of panels in this, but in the top row we see the size-mass relation for R20, which is 20%. In middle is for R50, and in the bottom is for the size-mass relation of R80. And from left to right is just increasing the redshift bins of the samples. So we compare them in different redshift bins. One thing which I should add is to say that we split the samples into star-forming and quiescent ones.
Right.
Yeah, so the blue ones are the star-forming galaxies in that redshift bins, and the red ones are quiescent galaxies, not forming stars. So if we just look at the star-forming at the top, this would be the size-mass relation of R20 sizes. For star-forming galaxies, looks like it's the same in most of the ranges, except that at very low redshift we see for the massive ones are increasing a bit. But the star-forming ones have a large R20 compared to the quiescent ones in all redshift bins. So this means that in quiescent galaxies, the concentration is higher of the stellar masses.
Nice.
But that's interesting that R20 doesn't change for the star-forming ones. And also, when we come to the half mass sizes, the second row, basically we can see that for the star-forming, we see the same behavior almost, except that for the massive ones above 10.5, they started to gradually the relation gets steeper. So that's interesting. But for the quiescent ones, we see a similar behavior for at all redshift. There is a high mass end slope, which is higher, and for this low masses, we have a relatively flat relation. And I would say that for the R80, which has a sizes of 80% of the galaxies, these two relations get closer together for star forming and the quiescent ones. That's interesting ones. And so, and if we compare it with the R20, we can see that this is a there's a big difference. So it means that the R80 is a bit less sensitive to the concentration or the Cersei parameters, etc. But cool. So that's but and the other point is that I hope that I won't forget the details sometime. But we also fit this. The lines are the best fit models. This, we have a broken power law model to fit into these median points, which are large symbols in these figures.
Okay.
And so when we just move, for example, to figure, I think 10 and 11, we could see, this was just the output of the paper, and this is a summary. I did figure 9, but figure 10 and 11 basically is showing how the best fit parameters of this size mass relation changes. The alpha in the is the low mass and the slope. This is for the low mass galaxies. We have the slope is almost flat. If you can see, it's almost 0. Yeah, for both systems, it seems that roughly constant with the redshift, and they don't change that much. Right. And it doesn't depend that much on the which sort of sizes that we choose. But interesting, for the star-forming ones, the high mass end started to increase when we come into the lower redshift beams, the beta ones. The beta gets steeper. I mean, for the massive star-forming ones, above 10.5, etc. When we come to the lower redshift beams, the relation gets steeper. And that's to some extent showing for all these sort of sizes. But this does not seem to be changed for the quiescent ones in the bottom panel of this figure, bottom right panel of figure 10, sorry. The other interesting point is that in the figure 11, in this broken power law relation, we have a pivot stellar mass and pivot stellar size that show at which stellar mass the relation changes the slope.
Okay, got it.
Yeah, and so this is interesting because in the right panels for both star forming and quiescent galaxies in figure 11, no, in the right panels, top and bottom, we see that this pivot mass actually is higher at higher redshift and is lower at lower redshift. So it seems that when we come to the late time of the universe, then the shift, the stellar mass that the relation changes is at lower, is lower.
Yes.
Comparing to the higher redshift ones. So that's what we can found from this analysis. So what the other step to show what we found is to look into the size evolution with redshift at fixed masses, which is in figure 12, basically.
Yeah.
Well, it's I can say that the left panels are for size evolution for R20 sizes, at different mass bins. If it's a very small ones in the bottom of each panel, which mentioned the stellar mass ranges, but it increased from top to bottom.
Yes.
So this say that at fixed mass, if we compare the size of the galaxies, are they increasing or decreasing, or how did they change? So when we look, for example, if we just look into the R20 sizes, the star-forming ones basically do not show any significant changes, the blue ones basically.
Yeah.
But for the quiescent ones, the most massive ones show a strong size evolution, R20. This is in the bottom panel.
Yeah.
Yeah, the massive ones.
Yeah.
For the low mass bins, the top two panels, it's a bit tricky, I should say. It has a, they show some sign of decreasing in the top, but we have to be very careful because when we study these galaxies at very low masses of this range and high redshift, a lot of uncertainties coming to play. So we should have a larger sample in future to make sure that are decreasing or not.
Okay.
But we do not. I think we they do not change that much. I mean, the evolution are fixed. I mean, at fixed masses. When we come to the R50, the half mass sizes, basically, for the star-forming ones, this is the same story. The size, there is a weak evolution of this sizes for massive ones. The bottom two bottom panels, basically. But the evolution is very weak.
Yeah.
But for the quiescent ones, we also see the evolution for our 50 or half mass sizes.
Yes.
The story is almost the same for R80. For R80, the interesting ones is that when we look into the star-forming ones in the bottom panel, the massive, most massive ones, we see that there is a fairly, a bit stronger evolution compared to it. And perhaps this is something to say that maybe something in outside the galaxies are happening. These stellar mass are assembling in the outside of the systems when we see this evolution.
Very cool.
But I should mention again that this is just comparing the galaxies at fixed masses, not looking into one galaxy, how it evolves with the redshift. So that's there's a difference between them because the galaxies might grow with the star formation, etc. But well, observation is you cannot trace one galaxy with time.
Right.
Right. We should go to the simulation.
Right.
This is we summarize this plot in figure 13, which I don't want to emphasize that, and we provide a table of the best fit parameters that we could.
Right, table 5.
Yes, and then in figure 14 would be also interesting to look is just the evolution of the Cersei parameters at fixed masses with the redshift. For the massive star-forming ones, these cross ones actually, if we look, we can see that the Cersei is growing with time, start to increase, which means that the bulges are building up basically in these systems. Above 10.5, these systems have showing a sign of the increasing of the Cersei parameters.
Yes.
But for the quiescent ones, it's hard to say that there is evolution. They remain roughly constant with redshift. although some of them are a bit noisy or there may not be enough samples inside that redshift means, but they're relatively flat and constant with redshift.
Okay.
So this is just somehow reflection of what we have found for the R20's evolution, and this is a complementary to that because R20 is very sensitive to the CERSIC index.
Yes.
So what we can say about all this is that maybe we have to compare this with the simulations to better understand. But for star forming ones, if we have a flat a specific star formation rate, so the galaxies grow self-similarly. So we could not see any size evolution at all. But for the massive ones, if the central ones be actually built earlier, then when the outside start to increase the stellar mass by star formation, or the specific star formation rate is increasing from center to the outside, then the outside might increase, and so we might see the evolution, especially in the outer parts.
Yeah.
So
cool.
This is something which is, for the moment, is to some extent in agree with what we see from observation of the star formation rate profiles of the galaxies. And so we might say that for the star forming ones, if they have a low mass, they might grow in self-similar way. But when they move to the higher mass range, then they might be a bit different paths for their evolution. For the quiescent one is a bit is a challenge, right? Because when we wanted to know how these galaxies grow, we have to consider that these sample of quiescent galaxies, that is redshift means, are a combination of the samples of star-forming galaxies which are quenched at different times. So some of the star-forming ones might quench, for example, 1 billion years ago. Some of them might quench 2 billion years ago. And so when they come into the at each redshift, when we compare them, then we have a mixture of the system. So we call it a progenitor bias of the systems. Okay. So we have to take into account this effect.
Yes.
But the question is that whether if the galaxies quench, then if this galaxy can grow in size or not. And many people propose that this might happen by minor mergers. Okay. The minor mergers can accrete to the outside of the galaxies, and so they can grow the size of the galaxies. R20, R50 and R80 can grow in this way. Right. So that can be a justification of why these galaxies can grow. But the rate of the growth should be checked, I think, when we could find a way how to trace back each, for a galaxy as a star, for the formation of each galaxy, which is very difficult in observation. And we have to actually look into the simulations to help us understanding this, basically this evolution. So that's just the main part of the paper and the science part, actually. Okay. The technical parts, which was to derive the stellar masses and how robust are the size measurements, the parameter measurements, is in the appendix, which I don't want to spend a lot of time. I'm running out of time, right? Or not?
Oh, yeah, we're fine. We're good.
Oh, okay, okay. But just I was very, I was trying to be very accurate in this way. So I thought to create a couple of thousand simulated galaxies and test them to see how robust that we can measure stellar masses, sizes, etc.
Cool.
That was shown in the appendix, and I think figure 19 would be interesting because when people compare them with the real objects, we would understand that these are simulated galaxies, which looks very similar to the yes, these are simulated galaxies, very similar to the basically observed galaxies.
Okay.
And so from that, we create a large sample of these systems and test the methodology. Also, I described in the appendix that we use another method for measuring the parameters, and these methods basically are consistent, show us a consistent results with the first method. So this is a relief to some extent, I would say.
Okay, you said right. It wasn't totally wrong.
The paper would be very long if I would have to say the first method and second method. So I decided to put all these technical parts in the appendix. It's large, but
okay.
That's what I would say about this work in half an hour that you said.
Okay, good. Moein, thank you very much.
Thank you
for walking us through this really lovely paper. Let's see. Let me go to the top. Let's get that title back. There we go. Galaxy size isn't equal to. So you hinted at a couple of times in the talk on you know, where things could go in, let's say, over a 5-year time scale. You mentioned the possibility of getting additional samples, particularly at higher redshift, comparing more to simulations. So where do we go? Where does this field go over the next 5 years, let's say?
Well, as I said, there are a lot of challenges that we have to, and a lot of questions that we have to address. The challenges is to get a larger sample and which are observed at longer wavelengths, so we can push this methodology, for example, into higher redshift beams, so we can trace back in a bit more longer period of time, especially above redshift of 2. It would be very interesting. So I think the next generation of the projects, for example, if the JWST would be almost about these things, and but also a couple of different surveys might provide us larger sample at higher redshift, so we can test this. Also, I think the IFU surveys will increase in the next 5 years, and so this would provide us not information about some stellar mass distribution, but also get the kinematics, which would be which we can combine to understand this.
Right.
And I think the simulations also growing fast, and we are very happy that we can compare them and understand how how the physics of the systems, which part of the physics are missing in the simulations or we did not understand. So I think we will have a good progress in the 5-6 years, I think, when the surveys come up.
Very cool. Very cool.
Yeah.
Lots of potential in us over the next 5 years. Very nice. Moein, thank you once again.
Thank you.
All right. Thank you, everyone. And we will see you on the next one. Bye-bye.